Hi, welcome to the course. I'm a data scientist, teacher, and consultant with experience in leveraging data to provide insights to many organizations, including Microsoft and the CDC. This course is designed to teach you hands-on practical skills for learning and implementing one of the most popular machine learning algorithms, random forests. These models are known for their power when it comes to both classification and regression tasks. So, how does random forest make decisions, and what does the structure look like? And how do you prevent it from becoming too complex? Together, we'll explore these questions. I'll walk you through the steps of building a random forest classification model using Python and Scikit-Learn. By the end of this course, you'll understand what a random forest is and how it works, when to use random forests, how to build and optimize random forests for classification, and how to evaluate and improve the performance. So, what is a random forest? It builds an ensemble of decision trees, combining their predictions to produce more accurate and robust results. Based on bagging, or in other words, Bootstrap aggregation, each tree is trained on a random subset of data with replacement, reducing overfitting. Only a random subset of features is considered at each split, creating diverse trees. Predictions are combined via majority voting for classification or averaging with regression. It handles both categorical and numerical data while reducing overfitting through diverse tree structures. So how, again, does Bootstrap sampling work? Each tree in the random forest is trained on a Bootstrap sample, which is created by random sampling with replacement. Since we sample with replacement, some original records may appear multiple times, while others may not appear at all. If the original data set has 100 records, each Bootstrap sample will also have 100 records, but about 63% of unique records will actually be used, and the rest will be duplicates. So, step by step, Bootstrap aggregation. Resampling with replacement, each decision tree is trained on a random subset of the data. The subset is created by sampling with replacement, and each subset is typically the same size as the original data set. Building multiple decision trees, each resample data set is used to train a separate decision tree. These trees are fully grown or pruned using maximum depth, or max depth, but trained on different data subsets. And aggregating the predictions for classification is what we're going to be focused on in this course. Predictions are combined using majority voting, so the most common class wins. And the usefulness of Bootstrap aggregation is that it reduces overfitting, it reduces variance, and it improves generalization, so it works well on unseen data. The splitting criteria. At each split, the algorithm evaluates metrics like the Gini impurity or information gain to choose the best feature. The feature that best separates the data into distinct classes is selected. Each tree grows until a stopping criterion is met, for example, max depth or minimum samples per leaf. This ensures trees don't overfit the training data. And for feature importance, random forests naturally rank features by their contribution to the splitting decisions. And we'll be using a confusion matrix to help determine the accuracy for our predictions that we'll be making with this random forest. It's a table used to evaluate how well the classification model is performing. It compares the actual versus the predicted values. Here's an example for the confusion matrix. Let's say you're predicting whether an email is spam or not spam. So a true positive, that means the model correctly predicts spam as spam. True negative, the model correctly predicts not spam when it's actually not spam. We have a false positive, which is a type 1 error when the model wrongly predicts not spam as spam. So it's a false alarm. And we have a false negative, or a type 2 error, when the model wrongly predicts spam as not spam. So this is a misdetection. Some key metrics from the confusion matrix is the accuracy, which is the overall correctness, and those are the calculations for each. Precision, how often is a positive prediction correct? A high precision means fewer false positives. Recall or sensitivity is how well does the model catch positives. A high recall means fewer false negatives. And the F1 score is the balance between the precision and the recall. A real world example. Imagine we're looking at COVID-19 testing. A false positive for a healthy person is a healthy person being wrongly told that they have COVID. A false negative is when an infected person is wrongly told they are COVID-free, which is very dangerous. So in situations where we're looking at medical testing, high recall is crucial. Catching all real cases is important. In email spam filters, high precision is more important, not marking real emails as spam. We'll also be looking at the receiver operating curves, or ROC, and the area under the curve. The ROC, the receiver operating characteristic curve, is a graph that shows how well a classification model separates two classes. It helps you visualize the trade-off between sensitivity, which is recall, specificity, at different thresholds. The AUC, or area under the curve, measures the overall performance of the model. So interpreting the ROC curve. If you have a perfect model, the curve reaches the top left corner, and it's a total of 1 under the curve, or area, and that means you have 100% accuracy. So the false positive rate is actually equal to 0, so no false positives. For a random model, this is essentially a diagonal line, which is a 50-50 guess, like flipping a coin. And a bad model is one where the curve dips below the diagonal, which is worse than just randomly guessing. AUC, or our area under the curve, higher AUC, which is closer to 1, means it's a better model performance. AUC, which that is equal to 0.5, means the model is random. And AUC less than 0.5 means the model is worse than the random. Again, as I mentioned, like flipping predictions actually may improve it. We'll also be talking about how we train and do a train test split on our data. It was used to split the data set into training and testing sets, and that the training set is used to train the model while the test set is used to evaluate its performance on unseen data. This helps prevent overfitting and ensures that the model generalizes well to new inputs. In this example that we're going to have today, we're going to be using the GridSearchCV. And the GridSearchCV is used for hyperparameter tuning. Before, we talked about the maximum depth of the trees, the number of samples, a number of leaves, and so forth. So minimum leaves, minimum samples. These are different knobs that we can tune, or parameters that we can actually tune to improve the model accuracy. When we use GridSearchCV, it finds the best combination of model parameters to improve the performance. It systematically tests different values using cross-validation, selecting the configuration that achieves the best results. Cross-validation is a technique used to test the machine learning model's performance more reliably by splitting the data set multiple times into training and validation sets. So instead of using a single train test split, cross-validation rotates through different portions of the data, training on some parts and testing on others. So a deeper dive into cross-validation, we're going to use k-fold cross-validation, which is the most common. And how it works is that it splits the data set into k equal parts, or folds. You train the model on k minus 1 folds and test it on the remaining fold. And we will repeat this k times using a different fold for testing each time. And then we average the results across all folds to get a final performance. So an example of a 5-fold cross-validation is that we'll split the data into 5 folds, train on 4 folds, test on the remaining 1, and then we repeat this process 5 times. Each fold gets a turn as the test set, and we compute the average accuracy across all 5 runs. And some things that we can tune to prevent overfitting, like number of estimators, which is basically number of trees. The default is 100 trees in Scikit-Learn. Okay, here we are in Google Colab. We're going to use Google Colab because it's just easy. We don't have to worry about the dependencies, package dependencies, and installation, because most of the most common tasks for machine learning have already been pre-installed in the Google Colab. And if you want the data set that I'm using here today, the used cars.csv, you can go right to the Enhance Impact website or in GitHub, and you can come here to decision trees. And this is from our previous course on decision trees, and get this used cars CSV and connect via Google Colab, or you can just download this data set. So here we can just download it and then upload it to Google Colab if you want. Okay, we're going to start with installing required libraries. GraphViz will be used for graphing these decision trees, which we don't really have to do with random forest, but I want you to just take a look at. We really can't see all of them, but it's a good way to take a look at what's actually going on underneath the hood. And here we're going to do our random forest with hyperparameter optimization and visualization. This is the name of this notebook. And here we're going to load our libraries. We're using NumPy to handle our arrays, pandas for the data frame manipulation, matplotlib and seaborn for visualization, along with GraphViz. Our one-hot encoder is going to be used to convert our categorical data into numeric format that the algorithm can use. You can't just use letters and And so we're going to convert that to a numeric format. Then we're going to use the random forest classifier. That's going to come from the sklearn.ensemble package. We'll use our import the model selection for our train test split and our GridSearchCV. And we'll have our sklearn.metrics for the confusion matrix and classification report, as well as the ROC curve and AUC to see how well our model performs. And then we'll also plot the tree. Here we loaded the data set, and we're going to look at the first 5 rows with data.head. And data.info is going to give us information about the number of records we have, how much of it is missing, what the data types are. So this is the data set, the first 5 records. It tells you the year, the make, and the model of the used car that we're looking at, the price, number of owners that there were, whether it was used for personal or multiple use, whether it was what kind of body it has, whether it's a pickup, is it an SUV, how much mileage it has, along with the price and mileage. This is the damage. Was there a damage, and was there an accident, and should we purchase it or not? And the purchased feature or column is our target feature. That's what we're trying to predict. Here it says we have 93 non-null records, and so none of them have any missing values. They're saying here that year is in an integer format, which is really categorical, but I'm going to use this year. We do some feature engineering so that we're not using the actual year, but they will be using the age. So we're going to create that. Also, another thing that I decided to do was to remove the accident column from the features that we're going to be using to create our model, because the damage and accident had a little bit of an overlap. So I'm just going to keep that damage and remove accident. So here's a subset of the data that we're going to be using. We're going to have our year. We took out the accident. And from here, I'm going to convert this year. We're going to change this. We're going to get rid of the year and create an age feature. So right now we're in 2025, the year. And so I'm going to take 2025 minus the year to get the age of the vehicle, the used vehicle. So now we've done that. We're going to keep the age. We remove the year. And so this is now the set of factors or features that we're going to be using for our model. The purchase feature is yes and no, and so is damage. So we go back to that original data set up here. You can see that damage is yes and no, and also whether or not to purchase is yes and no. And so we're going to do binary encoding, 0, 1 encoding for this. And so we're going to map no to 0 and yes to 1 here. So has it been purchased? If there's a 0, that means no purchase. Was a purchase a 1, that means yes, there was a purchase. So we're going to separate our data features into features and target. Here, our target is going to be the purchase column, and we're going to drop purchase from the rest of those factors that we have. So we're going to drop those. And so that is our X and Y. Our categorical columns are make, use, body. And then our numerical columns was going to be age, price, number of owners, and mileage. We're going to do one hot encoder on the categorical columns. And then we're going to convert these encoded data to a data frame with feature names. And the feature names are here. Get the feature names out of those categorical columns. Once all that's done, what we're going to do is we're going to put together, concatenate the numeric columns with the binary columns, which was the purchase and damage columns, with those other categorical columns where we had the make of the car and so forth. Okay, let's go ahead and run that. So here we got a chance to take a look at what this new final data set looks like, for at least for the the feature space, or for the factors. Here we have an age of the vehicle now is 14, 17 years old, 13, and so forth. The price and the number of owners, and then mileage. And then this is where we had the one hot encoding happening on the make of the vehicle. Make Audi. Was it an Audi? No. Was it a BMW? No. Was it a Buick, Cadillac, and so forth? Was it for rental use? Was the body a coupe, and so forth? Okay, here we want to continue with splitting the data now into the train test split. So here's our split. We're going to use random state as 40 to 42, which is a way to set the seed or make sure that this random shuffle is the same one that we use, so we can get the same results if we were to run this a second time. Here, the parameters or the hyperparameters that we're going to use is the number of estimators. Are we going to use 50 trees, 100 trees, 200 trees? The maximum depth, how deep will we go down? How many splits are we going to have? 5, 10, none. Minimum number of samples split. It's going to be 2, 5, 10, and so forth. Minimum samples leaf, 1, 2, 4. So we're going to test all of these. We're going to test the splitting criteria. We're going to go between using the Gini or entropy and determine of all these different combinations which ones is actually the best. We're going to initialize the random forest classifier, keeping our random state of 42 as the seed. And then we're going to use our GridSearchCV using this random forest classifier and that parameter grid. And we're going to use 5 folds. And what we'll be looking at is our accuracy for the scoring. And we have number of jobs equals -1. All right, and so we're going to do our fit onto the this training and the these X train and Y train. And we're going to look for the we're going to use the best estimator out of all of these, and we're going to print what those best estimators are so you can get a look at that, and then run the predictions. Okay, so let's take a look at it and see what happens here. It may take a little bit of time to run this because it has to go through splitting and training data 5 different times on these different combinations. Okay, so here we can see that our best parameters are the Gini for our criterion for splitting, having a maximum depth of 5. And the minimum samples per leaf is 1, with the minimum sample split is 2, and the number of estimators, basically 50 trees. All right, let's take a look at the accuracy. I'm going to calculate this confusion matrix and get our classification report. So here we can see that what we're getting for our total accuracy is 79. And you see what our precision and recall and our F1 scores look like. The ROC is 0.83. And so this is what we have here. If you want to view the first 3 trees, this is what our first 3 trees will look like. So here where we have damage, if there's no damage, we're going to go down this line and say, and it's in blue, so say this is the one we should purchase. It's about 49% have no damage, and 50% have almost 51% have damage. And so it shows here that if on this line when there is damage, that we're going to call this, don't purchase. This is a not purchase the vehicle. So 1 we're not going to purchase. When we come down here, this side says that do you have number of owners less than 3, less than 2.5? Then you go over here. If it's fewer owners, then yeah, we might be more likely to purchase. If there are more owners than that, we're more likely to not purchase. Here's the next tree. Again, this is a different type of split where you can see we're starting off with a new data. Let's say we got 100% of the samples, except now in this situation, 52% don't have damage and 47% have damage. And so here, this one says, hey, no damage. Come down here. Is it a Ford? If it's not a Ford, then yes, we can come here. If it is a Ford, then we're gonna stop here, and yes, we'll end up purchasing the vehicle. So 10% of the time we'll purchase. Okay, and these orange boxes indicate that there's not going to be a purchase. And so what happens in these ways, what happens is that the classification is just average when you're among all of these different trees. And again, this is 3, but the best parameters show that we actually have 50 of these trees. And of course, we're not going to plot all 50, but this is just an example of what you can do here. So I hope that you enjoyed this lesson on random forest, and definitely check out the video on decision trees. Give me a thumbs up, like, subscribe. It's definitely good motivation to keep me making these videos. Until next time, take care.